Hello, so this is going to be the video for how to model the wing with aspect ratio 12 and it's tapered at a zero point 0.7 ratio. And yeah, we're going to do a analysis of that wing shape through Xflr5. So if we go over here, right, let's take both of these out and let's load up, sorry, let's load up Xflr through here. And what we're going to do first is we're going to define the foil. So we're going to go here to direct foil design. And then we click foil, knock off foils, and this foil is going to be for 4412. We'll put the number of panels select around 400. Yep. And after that, we're going to go over here and um, we're going to first do the direct analysis for the airfoil. And typically when I go straight into the wing design before doing this, like the values will all mess up and stuff like that. So I just do this beforehand. So if we go over here to analysis, define analysis, and we could just put this to like 3 million. Yep. And then press OK. Sequence. Yeah, it's at from -5 degrees to 20 degrees. It's good. And then, yeah, after running this, then I can go and start the wing and plane design. And from the wing and plane design, this is where we actually get into finding plotting the tapered wing with the aspect ratio of 12. So we go here to define a new plane, remove fin and elevator, and it would define the main wing. So over here, to define it, for this wing, we have to make sure that the aspect ratio and the aspect ratio is 12 and the taper ratio is 0.7. So if I go over here and say offset, put this to 0. And the chord length, so the root chord length is supposed to be 1, so we're going to put when y is equal to 0 to 1, and then we're going to put this to 0.7. Now, as you can see, in this program, the taper ratio is backwards. So instead of having, the program takes, the, instead of having CT over CR, it has CR over CT. So it kind of messes it up and puts it as 1.43 instead of 0.7. Even though that's, obviously like it should be 0.7 for the taper ratio, but it's fine. We'll just take care of it for now. And to increase the aspect ratio, we're going to increase the span of the wing to around 5.1. That should give us, yep, that should give us 12. And then we save and close it. After doing this, we just press OK. And should load up. It's not loading up. Hmm, interesting. Oh, okay. We were supposed to define analysis. Sorry, I forgot. So we put the free stream speed to 30 meters per second, just to make sure that we're using a lifting line theory for the wing. Make sure we use that analysis method. Everything here seems right. Yep. And now we start from -5 degrees to 20 degrees and we increment by 1. So if we analyze here, can I find the wings foil? Oh, sorry. Okay. So before we do that, let's go to current plane. We're going to edit the wing. I forgot to do this. Identify the foil. There we go. That was my bad. So now we go here to analyze. We'll just make sure. Yeah. Yep. Overwrite that just in case. Analyze this, and here we go. As you can see, now it's properly, not that the value is properly loaded up. We can see the lift in the indicated drag, the viscous drag and the downward velocity at every angle from -5 to 20, as you can see here. And now to calculate these values in here, let's see, um, it's supposed to show, is it not showing? Say graph scales. Hmm. Okay, it's not showing for some reason. Okay. Well, you know what we're gonna do? I'm gonna show you what these graphs look like since they're not running. So if we go over here to here. Oh, no. Let me open the project. It's gonna be this wing. We see the graph scales here. Okay. So after you load that wing up, these are the CL and CD values that you get, and then CL the coefficient to alpha, the induced drag to alpha, CLCD alpha. But we need these three graphs right here. And then if you go over to this panel, it shows various graphs. So we have the lift coefficient, local lift coefficient along the span of the plane, which is good to find the local values later in the graph. And we can also put another graph, which we can do induced angle, or we can do the, where is it? Induced angle, local lift coefficient right there. And we could also do the induced drag coefficient. And getting these values, you can then put them into Excel, right? When you come here, I put, so I took all the values of the graph. So the angle of attack with respect to lift coefficient, angle of attack with respect to lift coefficient over drag coefficient, the graph with respect to CDCL, and then span over the induced angle of attack, span over induced drag, span over induced the local lift coefficient. And using those values, I created these graphs over here. So this was respect to wing E, which, so if you look at wing E, this is the graph for it. These are the graphs with respect to the other wings. But yeah, wing E is the same tan color. As you can see, the graphs look pretty accurate. And for CLC, lift coefficient over drag coefficient with respect to angle of attack, that's the value as well. And then to find the theoretical values for the wing, I basically I took the lift coefficient at 5 degrees, and then I found the efficiency values for the taper ratio, and using that, and to find the value, I basically went to the Oswald efficiency graph, and when knowing the aspect ratio and the taper ratio, I found the efficiency value, and then I found the induced drag coefficient from that, which is, yeah, it's basically lift coefficient squared divided by pi times the efficiency value times the aspect ratio. And I found the lift at zero, which what it basically did was I went over here to the wing, and I went to where the lift went from zero to from negative to positive, and I interpolated between the angle of attack and the lift coefficient to find the zero lift angle of attack. And then for this in this drag, the I basically took the lift coefficient. Oh no, sorry, not the lift coefficient. I basically took the um geometric angle of attack minus the zero lift angle of attack minus the lift coefficient over 2 pi. And then for the effect coefficient, the I subtracted geometric angle by the induced angle. For the downwash velocity, I got the induced angle and I multiplied it with Bet's free stream, which was 30 degrees. And for the simulations, I basically took the simulations that I get from, sorry, these graphs right here, the induced drag graphs. So I basically took all of that and I converted them into graphs over here for Excel for the induced angle of attack over the span. For wing E, it's the yellow lines. And for local coefficient, the same thing. For wing E, it's the yellow. As you can see, it lines up pretty well. And for induced drag coefficient over the span, it also makes sense as well for wing E. And then there's also the downwash velocity, which is pretty much proportional to the angle, the induced angle of attack. So it goes to show why the graphs are very similar. And yeah, that is basically, oh, and the lift curve slope. For wing E, basically, what we did was get the linear trend line for wing E and basically took out the equation in Excel and took and then you get the variable from that, and that's how you get it. That's how you get a lift coefficient. And then we compared to the theoretical one, which was, let's see, right here, which was we basically input it into the equation found in the notes. And yep, that is basically it.